So good morning, everyone. Thank you very much for coming today, or for the time to let me do my presentation today. So today I'm gonna talk about this paper published by T.B. Jones, whose name is More About the Electromechanics of Electrowetting. This paper that was published in the Mechanics Research Communication, and we're gonna discuss a little bit about the content of this paper and the main outlines that it contains. So here we can take a look at the main different parts of the article, starting with an abstract, then the introduction, then the author introduces the definition of the sessile droplet, or the leaky droplet, that we're going to explain later more in detail. And then he discusses a little bit of the electromechanics of the deformation of a liquid droplet, and then a little bit about the equilibrium, the electromechanical equilibrium. And then he starts defining how this electromechanical equilibrium or this electrowetting behaves in cases where the water or the liquid droplet locates in between two electrodes or dielectrics. And then the next part of the paper discusses a little bit the cases where we consider a three-dimensional droplet, that is actually the situation that we might encounter like in reality. Nevertheless, in this part of the paper, the author mentions, again we will discuss this a little bit more in detail later. He mentions that one of the main aspects of this electromechanical study is the fact that we can actually study all the general cases, the three-dimensional cases, as if it was a 2D case. We can make the assumption. Then at the end he introduces the frequency-dependent droplet electromechanics and the limits of this consideration, as we were going to see later on. So in this article, a classical long parameter electromechanic model is presented that is able to describe the phenomena behind the drop-based electrowetting, but it is also extended to cases where the electrical field that is produced in a dielectric is no longer uniform, that we will explain later. That is called dielectrophoresis. So the main key, or the importance of this approach that is presented in this article, is that it will be able to make the link between the electrical phenomena and the mechanical phenomena behind the electrowetting, by the fact that the electrical phenomena is described in terms of the capacitance, or expressed in terms of the capacitance. So this is very important because the capacitance is a variable that no longer depends on, for example, the contact angle, the difference in the geometry of the water or the liquid drop, and is not dependent on fringing fields, which makes this electromechanical model very easy to use. So I consider very important to mention the more important words, or the important keywords that are presented in the article by the author, in order to better understand the physics and the mathematics that is behind this approach. So the first one that is mentioned in the article is the lump parameter. So it's basically a system in which the dependent variable that we are studying, it depends only or is a function of one single variable, whether time or space, but not both at the same time. So the next term is the EWOD, that it stands for electrowetting on dielectric. That maybe we're a little bit familiarized with this term because it's what we have been studying in the course of microfluidics. So the next term is DEP, that stands for dielectrophoretics, which is the case that I explained a little bit before. It's the phenomena when we that we observe when the force that is exerted on a dielectric particle is subjected to a non-electric field that varies whether on time or on space. These cases we might not be a little bit familiarized with, because so far what we have been studied are cases when the electric field that is generated is constant. So the next term is the fringing field. To explain a little bit about what the fringing field is, we have to understand the fact that when we have a voltage difference that is induced in between two dielectric, we know that an electric field is generated. This is what happens actually in the case of a capacitor. So nevertheless, in reality, it might be observed that the electrical field that is generated in between the two dielectric, it does not only exist in the place between the two dielectric, but also some distance away. So this electrical field that is generated some distance away the dielectric is what is called fringing field. And the last term that I consider very important to remark is the impedance. So this is actually the opposition of a system or a circuit to alternative current AC. I do apologize because there is a mistake here in the slides. I put the electric current as well. Nevertheless, this is wrong because actually that's the difference between the impedance and the resistance, or the resistivity. Because the resistivity is actually the opposition of a circuit to DC current. But the impedance is the opposition of a system to AC current. So this must be deleted. So in the next part of the article, the first part is in the introduction part. The article, he wants to emphasize the importance of developing efficient and predictive models that help us to better describe this phenomena that is behind the force that are induced in electrowetting and electrophoresis, because these are fields that have been very fast developed in the last years, especially in applications like microelectronics. So where every day the schemes that are used and the configuration of the electrodes are very complex. So this is actually one of the main challenge this kind of models and physical models are facing, the fact that the structures and the geometries that have been used in the last year might not be very simple. So all the models that are going to be developed in the future or in the incoming years have to take all this into consideration. Also, for example, the classical model of calculating the electrical force on a droplet in electrowetting devices, it refers mainly to the fact that the voltage changes that are induced in a water drop or in a liquid drop are basically enhanced to the surface force in the contact angle. So this is actually might not be true in reality, because it has been shown that the variation of the contact angle that we have seen in the course of microfluidics, and also the variation or the movement of the center of mass of the drop are distinct observable. Like it might depend on the electrostatic force on the liquid's free surface. So with this being said, we might identify the main objectives of the article. So the first one we could say that is to extend the electromechanical interpretation of electrowetting to cases where the geometry of the liquid drop might not be that simple, or the geometry of the electrodes also are complex. It is also one of the main objectives of the article to remark the importance of developing a physical model a long parameter capacitive model, which can be able to predict the frequency dependent behavior of electrowetting geometries, especially when in the cases where the electric field that is generated might not be constant, so it will vary. And also the main objective might be as well to cover the gap that the models that are based on the contact angle have, because in these cases they don't consider cases where the where the frequency is also an independent control variable, or the cases where the geometry of the water drop is not it's not that simple. So first we have the definition of a sessile droplet or a liquid droplet. As we can see in the figure, it's basically the case where we have a liquid drop that is settled on an electrode. The drop initially is considered to be spherical. After we induce an electric field due to a different voltage on the electrode, it will cause the deformation or the movement of the water drop. As we can see here in the darker figure, is the shape of the drop after the electric field is induced. So in this case, actually the particle or the drop will behave as a capacitor due to the electric charge movement that is induced after the electric field is generated. So this is basically the case that we have observed in the course of microfluidics, where we can see, for example, R, A, and theta are the main parameters: the contact angle, the radius of the drop, and the contact distance. If we can see the distance from the center of the electrode to the point of contact in between the drop and the electrode. It will initially be denoted as constants, but then it will vary because of the introduction of an electric field. So, as I mentioned before, this analysis will assume that the shape of the drop will be completely spherical. So this assumption will be valid by establishing the relation between the gravitational force that is acting on the drop and the capillarity. So this relationship that is called the bond number is defined as BO, as we can see here in the slide. So basically, in these cases, we will consider that the capillarity will be way larger in comparison to the gravitational part of the gravitational force. So it will make the bond number very, very small, so smaller than 1. So for these cases, we can actually assume, or we can actually see as valid, the fact that the water drop will have a spherical shape. If we start from the assumption that the volume of the drop doesn't change after the let's say the induction of an electric field, so it makes the drop will deformate, but however the volume doesn't change, it will lead us actually to make some relationship between these parameters that we have established before. So like for example the three equations that we see here, as I mentioned, for example, if we say that the volume is fixed, so it will not gonna be it's not gonna change, so we can set the relationship, for example, of the volume before and after the deformation, that this will be equal. So by setting this equality of the volume, it will lead us to these equations that we can see here. So if we consider the hydrostatic of the droplet in the absence of an electrical field, it means when the voltage difference is equal to 0. We can denote that two parts of the surface area. So the first part we will denote it as the spherical surface area. It will be the area of the spherical surface of the drop, the one that is in contact, the liquid and the gas or the vapor. In this case we will denote it by ALB, and we can also consider the surface area of the droplet that is in contact with the electrode, that will be denoted as ALS. So we also introduce the definition of a surface total surface energy, which will be denoted as the W gamma. So we will be in this case we will relate the term of the surface tension multiplied by the area of the complete droplet, as we can see. So as we can see, it is a function of A, that is actually the horizontal distance between the center of the electrode and the last point of contact in between the droplet, the surface droplet, and the electrode surface and the vapor, in this case the gas. So as we have seen here, the total surface energy is expressed actually in terms of A. So this is the mechanical variable that have been chosen, since A is the we can say the horizontal parameter, or the horizontal distance in between the center of the electrode to the contact point or the contact line between the drop and the electrode, and also the gas phase. It allows us to actually compute an effective interfacial force per unit length that is going to be defined. So if we replace all the terms in the equation of the force, all the terms that we have been seeing here, the derivative of the surface energy as a function of A, we are going to basically obtain this equation that is the Young equation, as we already know. So in the next part of the article, the author analyzes the electromechanics of the droplet deformation. So in this case, now the voltage induces an electrical field that will end up by deforming the droplet shape. So in this case, now we're going to consider that actually the droplet will behave as a capacitor together with the electrode, or with the dielectric. So in this case, we analyze the part that is in contact, the part of the droplet that is in contact with the surface of the electrode. It's going to be called ALS, and again the droplet is going to be considered as spherical. So, but in this first part of the electromechanics of the droplet deformation, the dielectric is considered to be very thin. So the electrical field that we mentioned, that is called the fringing field, can be neglected. So in this case, D, that is actually the thickness of the dielectric, is going to be considered very, very small in comparison to the horizontal distance that the droplet deformates. So it would lead us actually to the equation of a capacitance in this case. However, in this case, this equation is only valid is if the shape of the droplet at the moment of the deformation is considered to be circular. However, in the cases where the thickness of the dielectric might be not that small, so if we consider the cases where the horizontal displacement or the horizontal deformation of the droplet is more or less equal to the thickness of the dielectric, then in this case the fringing field that is originated might not be negligible, and it can no longer be ignored. So in this case, a correction factor might be included So the author in the article, he mentions and he introduces the correction factor um, of the capacitance equation, citing the research of Plumsey and Collin. So we got the equation 6, that is actually the corrected equation of the capacitance as a function again of the horizontal deformation. So once we have a function that allows us to compute the capacitance in terms of A, in this case the horizontal displacement of the liquid drop, the author introduces the concept of the energy conservation condition, which is basically the coupling between the electrical force that is generated and the mechanical force that will cause the deformation of the drop. So it would lead us to the next equation, where Q is basically the electrical charge, that is basically the capacitance multiplied by the voltage, and WE will be the electrical energy storage of the coupling that will depend on Q and at the same time on A. So in order to better manipulate this equation, the author he uses like a mathematical tool, transfer function that is called a Legendre transform. So to better have an idea of what a Legendre transform is, we can, for example, make an example of a function f of x. We can say that this function represents energy, for example, like in this case. So this transfer function comes into play when we want to switch the way we actually look at each one of the values f of x, and instead we want to take a look at the cost of those values, if you want to see it like that. It's like changing the way of seeing a function, something like that. And how do we do that? So for example, in these cases we have to introduce a new variable, let's call it p. So we calculate p of x and we subtract f of x, and then once we do that, we find or we maximize this function. So basically it's finding the maximum value of this multiplication of p by x and subtracting the new function. This maximization will lead us to a new function that we will call, for example, f prime of p. That is a new variable. So essentially, in simple terms, it's like taking a look at the profit that we get when we take a unit of x and we subtract the actual cost or the actual energy f of x. So it's basically like a new function that tells you the maximum profit or the maximum profit that you can get or you can gain for each energy value at a certain level p. So yeah, it's a little bit complicated, but it's a useful mathematical tool that the author uses in this part in order to define like a new term that he calls co-energy, that it's expressed, as we can see here, WE prime, that in this case will no longer depend on Q, but it will depend on the voltage. That at the end, that's what they want, because as we can see before, Q depends on A. We cannot have like a function that depends on A and another function that also depends on A, so it will be now mathematically complicated to use. So at the end we will have a new function that will depend on the voltage and A. So it will be defined as the electrical charge multiplied by the voltage. So using this new concept in the last equation that we had it before, it would lead us to the next equation, that is Q dV instead of having V dQ. So then we can define a kind of an initial defining condition on the electrical force that would mean that the electrical force will be equal to 0 when the voltage is equal to 0. So by defining this, the last equation can be integrated into space, so we can obtain the next equation. that WE prime will be equal to 1.5 of the voltage squared multiplied with the capacitance as a function of A. So what does it mean? It basically means that at the end that the electrical force can be computed as the derivative of this co-energy function as a function in with respect to A, evaluated at a constant voltage difference in this case. So at the end, the electrical force per unit length at the constant line can be defined actually as a function of the mechanical variable A that we have introduced by setting the next equation where the voltage obviously depends of A. So in the next part of the paper, the author mentions the electromechanical equilibrium. So now once we have defined the where we have introduced the electrical force definition and the mechanical force that we defined in the first part by the hydrostatic equilibrium equation, if we can say it like that. But we can say that the sum of both forces will be equal to 0 by electromechanical equilibrium. So after that, then we can make some mathematical manipulation that will lead to the next equation. So this equation is actually called or known as Bert's equation for voltage dependent apparent contact angle on dielectric coated electrode. So as we can see here, basically the derivation of the electrical force, it requires absolutely no knowledge of the hydrostatic profile of the liquid drop or either the contact angle. So in the next part, the author introduces the case of electrowetting, where we use two different electrodes, coplanar, both of them, separated by a gap. It's denoted by G in this case. So in this case, we define the part of the drop that is in contact with the electrode 1 by L minus X, and we denoted the second part of the surface contact by L plus X. So in this case, the capacitance per unit width on the left and right hand side of the droplet can be defined basically by the next equations. In this case, in the droplet is not grounded, the net capacitance is the series combination of both capacitance, and we can define like a total net capacitance by the next equation, where C1 and C2 are the capacitance in the first in the left hand side, and C2 is in the right hand side. So using the same co-energy definition that we have defined before, where W will be defined as the capacitance multiplied by the voltage squared 1.5. In this case, we can again compute the electrical force by setting the derivative of this co-energy function as a function of, in this case, the x or the horizontal displacement evaluated at a constant voltage value. So if we compare, if we remember the last equation that we got for the electrical force at the surface contact per unit length that we defined previously, let me go back to remember this. By setting the energy conservation condition, we got to this equation of the electrical force. So that is this equation. Now we can define the capacitive voltage, the voltage drop across the layer in both sides of the drop that are in contact with the two different electrode 1 and electrode 2. So in this case, we can define the voltage in the first part, and then the voltage in the second electrode in terms of the capacitance, as we can see here, and then the total electrical force can be computed at the sum of the vectors in the term in the right and the left hand side. So we will at the end, it will lead us the next equation. So now in the next part of the article, the three-dimensional case is introduced. So now we no longer consider the liquid drop as 2D, but now we're going to take into account the fact actually the same case as before. We're going to have the two electrodes and the liquid drop in between both of them. They are divided by like a gap or a space that is denoted by G. But in this case, we're going to take a look at the 3D case. So in this case, as we see in the figure, this is like a top view of the droplet, and we're going to assume the case where the displacement is going to be in the same direction, in the x direction. We can consider the case of the deformation, since which is going to be in the horizontal direction. We can see that actually the change of the shape of the droplet would be denoted by dA1 for the case on the left hand side, and dA2 of the change of the shape surface and the second electrode will be denoted by W dx, where W will be considered as the width of the droplet, and the x the change, the elementary change in the horizontal direction. So as I just mentioned, we will consider an irregular droplet standing between two electrodes separated by the gap. So we can just make the same assumption that we made before, and we're going to consider that the shape will remain fixed during the translational motion along x in the x direction. So in this case, the derivative of the capacitance dc dx in the left hand side and in the right hand side will be independent of the position. They will be equal in magnitude but opposite in sign, since it will be in the opposite direction for the left part. So we can consider the dc dx in the next equation. So we can define actually the two contributions of the electromechanical force as we have defined it before, as the contribution of the first part and the second part of the drop. The first one that is in contact with the first electrode at the left, and the second one as the electrical force that is in contact with the second electrode. So if we substitute in these equations that we see here, in this equation that we see here, the value for V1 and V2 that we obtained before in this part in terms of the capacitance, we are going to basically replace it in this equation. So, and if we make some mathematical operation, we can actually see that we're at the end we're going to obtain the same result that we obtained for a 2D assumption that we saw before. So actually it shows that the droplet outline has absolutely no influence on the net electromechanical force. So that every like 3D configuration can actually be seen as a 2D one. So basically at the end in the paper we're going to consider like the more complex case, that is basically like a coupling of the other assumptions of the other model that we have been studying. So in this case we're going to analyze the case where the voltage is no longer constant. So we have a fluctuation in voltage. We will actually have instead of having a DC circuit, we're going to have an AC circuit. So we're going to have the case also with the two electrodes that we saw before, separated by the gap, and the voltage that is no longer going to be constant. So in this case the electrical field that is going to be generated is no longer uniform. So the liquid or the liquid drop in this case is no longer going to behave like a perfect conductive liquid, but in this case it's going to be semiconductive, since due to this variable electric field that is going to be generated, the drop is going to have a certain impedance or just certain resistance to this to the current that is going to be generated. And also due to this let's say non-constant voltage difference, also the dielectric coating is going to experience a certain capacitance, as well as we can see here denoted by CD and CD1 and CD2 for the two different electrodes. So when we're describing or studying this more complex scenario, we can actually tell that the electromechanical model that we have been studying before, or that we exposed before by the author, it's just difficulties by only using our RC circuit model if we want to introduce now a change in the distribution of voltage. So in this case, the approach that the author is going to use, or that he implements, it assumes that the voltage has a sinusoidal form described as this function, where B bar is going to be defined as the phasor voltage, and the imaginary part is going to be denoted by J, and W will be the radio frequency. So again, this is going to be a complex function depending on time. It would also be considering the case where the W exceeds the frequency of any observable fluid's surface disturbance. So, and also only time average of electrical forces. So in this case, we can denote G as the separation between the two electrodes, and capital D will be the distance between the copper and the dielectric coating, so between the two electrodes. Well, in this case, due to the case that we're going to analyze, it's going to be 3 electrodes actually. So we're going to consider again in this case the scenario where the thickness of the dielectric coating is going to be very small or negligible. So at the end, it will basically mean that the fringing field is going to be negligible. So at the end, we can compute the capacitance and conductances per unit width. By for example, the capacitance, we can compute it as we can see here, just as we shown before. Now the distribution of voltage among all these 4 capacitive elements that we defined in the figure, it can be obtained using impedance division. So we define the 4 phasor voltages, B bars, already discussed, across all these elements. So we can define it as here as a function of Z, where Z are actually the complex impedance of each one of the elements. So just to remind, the impedance is defined as the resistance of a material to AC voltage. So basically, we can define again like an electrical force structure per unit width as we defined it before. So if we remember, we defined that the electrical force is going to be 1.5 the voltage multiplied by the voltage squared multiplied by the capacitance. So as we saw in the first scenario, in the simplest case, but in this case, since we're going to have the 4 capacitance elements, so the total electrical force is going to be calculated as the sum of all the 4 vector elements of these capacitive elements. Sorry. So as we have defined here. The only difference is that now we're going to, instead of having the voltage term, we're going to have the phasor voltage, that is V var, and the derivative of the capacitance of each one of the elements as a function of the x. So if we combine in this equation, if we put all the terms that we have already computed, for example, the phasor voltage, we have already defined them in this equation. So that as a function of the of each one of the impedances. So if we replace each one of these terms in this equation, at the end we're going to have this maybe very long equation that we can see here. So however, if we can see this in this equation, we can observe two important things. One, the first thing is that there is absolutely no dependence of the electrical force in this case. For example, on the contact angle. So we see absolutely no contact angle on the equation. There's also only a function of the voltage and of course of the horizontal displacement. And the second thing that we can observe the equation, for example, maybe to have a physical interpretation, is that we can define like two different behaviors in terms of the frequency W. So we can divide the two different phenomena into low frequency or high frequency. So for example, in cases where of a low frequency, we will have an electrowetting behavior. So we can express the electrical force just as we express it in the first cases, as a 2D, just the electrowetting case. Those are the cases where W is very small in comparison to sigma, and as the ratio between sigma, kappa, and epsilon to 0. So in these cases, this long equation simplifies to this. That is exactly the same equation for the electrical force that we got for the 2D no variation of voltage case. However, what we have high frequency behavior, well, the equation will be described by this term. It's going to be a little bit more complex. So these are the cases basically of high frequency. So these are the cases where we have a very high variation of voltage. So basically at the end, the author, like, he divides these two frequency cases into, for example, the first, where the frequency is very, very low, we can say that the liquid, or the liquid droplet, it behaves as a perfect conductive a perfect conductor. So in this case, there's no variation of voltage. The electrical field that is generated is completely uniform. So a perfect conductor, there is absolutely no impedance. And the second case would be the case where the liquid drop will behave like a perfect insulator, where W tends to infinity, for example. It means that the impedance will tend to be very, very big, so it will not allow, or it will be very resistive to the AC voltage. So at the end, we can get some main conclusions in the paper. So the first one, the electromechanical derivations that are presented, they have absolutely no dependence on the contact angle or the liquid profile of the drop at the contact line between the surface, and they also have no dependence on fringing fields that are considered negligible in these cases, where if the thickness of the dielectric is considered as very, very small. The accuracy and the modeling efficiency depend only on having very good information about the derivative of the capacitance and the distribution of voltage in this case, um, but absolutely no dependence on the contact angle. So this information is the key to better understand why the capacitive model works. So net translational displacement, in this case on the horizontal displacement of a liquid droplet, will affect the differential system capacitance, and this capacitance will basically behave or have a linear relationship to the energy of the system. So the last conclusion that we can see is that this electromechanical model can be utilized to predict shape changes of virtually stationary liquid masses, as long as the geometry is not complex. However, one might argue that the contact angle model, it can be enough from an engineering point of view. As we mentioned before, there are some cases, as the one that we mentioned, where the frequency is very low, so we can consider actually the case of an uniform electric field, so we can consider actually an electrowetting model depending only on the contact angle. We can neglect all the variation of voltage if the frequency is very small. So thank you very much for the time and for listening to the presentation. And if you have any questions, any comments or feedback, please do not hesitate. Thank you.